The 100-mile railgun tried to punch through air once at Mach 7, then it died. Scramjets try to live at Mach 10 by burning fuel in air that behaves like a concrete wall. Boost glide vehicles skip the engine entirely and just surf that wall for thousands of kilometers. Both stay hypersonic, but only one actually works in combat right now. You clicked because Mach 10 engines that defy physics sounds impossible. It nearly is, which is why the weapons countries are actually building don't use engines at all. In 14 minutes, you'll understand how scramjets try to breathe air at Mach 10, why that's brutally hard, how boost glide vehicles avoid the problem entirely, and which approach is winning the hypersonic arms race. No hype, just physics, the engineering limits, and the weapons that actually work. Stay with me. Alright, let's establish what we're comparing. Scramjets, air-breathing engines that try to sustain hypersonic flights by burning fuel and supersonic airflow. No moving parts, just controlled combustion at Mach 5 to 10. Boost glide vehicles, rocket launch projectiles that glide through the upper atmosphere at hypersonic speeds. No engine, just physics and heat shielding. Here's the fundamental difference. Scramjets try to power through hypersonic flight by extracting energy from the atmosphere. Boost glide vehicles get all their energy from a rocket, then coast, using lift and maneuverability to extend range. One is an engineering challenge, the other is a physics exploit. Here's the race. Countries want hypersonic weapons, missiles that fly so fast and maneuver so unpredictably that current defenses can't stop them. Scramjets promise sustained, powered hypersonic cruise, potentially thousands of kilometers of controlled flight. Boost glide delivers that range today, with proven technology but with less flexibility once launched. The question is, which approach actually works in combat? Here's what we're covering. First, why air at Mach 10 acts like concrete, the physics problems both systems face. Second, how scramjets work and why NASA's X-43A only flew for 12 seconds. Third, how boost glide works and why it dominates current arsenals. Fourth, the trade-off, engines versus no engine, sustained flight versus one-shot glide. And fifth, which approach is winning and what that means for missile defense. By the end, you'll understand why the hardest engineering often loses to the smartest physics. Let's go! Why air at Mach 10 acts like concrete. Alright, before we talk about scramjets or boost glide, we need to understand the problem both face. Air at hypersonic speed stops behaving like air. Here's what happens at Mach 10. Air molecules can't move out of the way fast enough. They compress into shock waves, sudden, violent pressure spikes. That compression generates enormous heat, thousands of degrees Celsius. At those temperatures, air molecules break apart, dissociation, electrons strip away from atoms, ionization. Plasma forms around the vehicle. The air becomes a glowing, electrically charged barrier that blocks radio communications, absorbs radar signals, disrupts GPS, creates drag force measured in tons. Here's an analogy. Imagine running into a swimming pool. Walk slowly and the water parts easily. Sprint at full speed and the water feels like hitting a wall. That resistance is drag. Now imagine sprinting at Mach 10. The water, air, can't move fast enough. It acts like concrete. That's the hypersonic regime, and it's where both scramjets and boost glide vehicles have to survive. Here's the temperature problem. The leading edge of a hypersonic vehicle can reach 2,000 degrees Celsius at Mach 5 and 3,000 degrees Celsius plus at Mach 10. That's hotter than most metals' melting point. Materials that can handle it? Carbon composites, ceramic heat shields, exotic alloys with active cooling. All expensive, all heavy, all prone to failure under stress. Here's the pressure problem. Shockwaves create pressure differentials that can rip control surfaces off, crack heat shields, destabilize flight. And here's the control problem. At Mach 10, you're covering 3 kilometers per second, 180 kilometers per minute, and 10,800 kilometers per hour. Small adjustments at those speeds create massive forces. Overcorrect slightly and you tumble out of control. Both scramjets and boost glide face these challenges, but they solve them in completely different ways. Section 2. Scramjets, breathing at Mach 10. Alright, let's talk about scramjets, because the idea sounds simple until you try to build one. Here's the concept. A scramjet is a supersonic combustion ramjet. No turbine, no compressor, no moving parts. How it works. Air enters the inlet at hypersonic speed. The inlet shape compresses the air without slowing it below supersonic speeds. Fuel is injected into the supersonic airflow. The fuel-air mixture burns while still moving supersonically through the combustor. Expanding exhaust gases exit the nozzle, producing thrust. Here's why that's insanely hard. Problem 1. Millisecond combustion. At Mach 10, air passes through the engine in milliseconds. Fuel has to inject, atomize, mix, ignite, and burn completely, all in the time it takes to blink. Problem 2. Supersonic mixing. In subsonic engines, turbulence naturally mixes fuel and air. In supersonic flow, there's no time for turbulence. Fuel and air streams pass each other like ships in the night. You need precise injection angles, multiple fuel ports, and clever aerodynamic tricks to force mixing. Problem 3. Staying lit. The combustion has to be stable despite varying air density, shockwave interactions, and inlet pressure changes. Any instability can blow out the flame or choke the engine. Problem 4. Thermal management. The combustor walls experience direct flame contact, shock-heated airflow, and radiative heating from plasma. Materials melt, cooling systems fail, engines disintegrate. Here's the X-43A record. NASA's X-43A remains the gold standard, a scramjet powered test vehicle that hit Mach 9.6 at 33 kilometers altitude in 2004. Here's what actually happened. A Pegasus rocket boosted the X-34A to hypersonic speed. The scramjet ignited and sustained combustion for roughly 10 to 12 seconds. Then it shut down, glided, and eventually broke apart. Total powered flight time at Mach 9.6, about 12 seconds. Here's why that matters. 12 seconds is proof of concept. It's not a weapon. A hypersonic cruise missile needs sustained flight, minutes, not seconds, to reach targets hundreds or thousands of kilometers away. No scramjet has ever achieved that publicly. Here's the current state. The US X-51 Waverider extended scramjet flight to about 200 plus seconds at Mach 5. China and Russia claim scramjet progress but haven't demonstrated sustained Mach 10 flight publicly. Scramjets remain experimental, stunning in labs, elusive in arsenals. Here's an analogy. A Formula One car hit 230 miles per hour on a racetrack with perfect conditions, expert drivers, and a support team. Try driving that car through a war zone with potholes, debris, and enemy fire. It won't last long. Scramjets are F1 cars. Boost glide vehicles are armored trucks that just work. Section 3. Boost glide, surfing the atmosphere without an engine. Alright, scramjets are hard, so what's the alternative? Boost glide vehicles, which skip the engine problem entirely. Here's how boost glide works. Step 1. Rocket boost. A conventional rocket motor, proven, reliable technology, launches a hypersonic glide vehicle, an HGV, to the edge of space. Peak altitude, 40 to 100 plus kilometers. Peak speed, Mach 5 to 20 plus, depending on design. Step 2. Separation. The glide vehicle separates from the rocket booster. No engine, no fuel, just a shaped body with control surfaces. Step 3. Atmospheric re-entry and glide. The HGV re-enters the upper atmosphere at a shallow angle. Instead of plummeting straight down like a ballistic missile, it generates lift, like a hypersonic airplane without an engine. Step 4. Skip and maneuver. The HGV can skip off the atmosphere like a stone skipping on water, maneuver laterally to evade defenses, and adjust trajectory to hit moving or hardened targets, all while moving at Mach 5 to 10 plus. Here's the physics. The HGV isn't fighting physics, it's exploiting it. Lift. The wedge-shaped body generates lift from high-speed airflow, allowing controlled glide. Drag. Intentional drag bleeds off speed in a controlled way, extending range and allowing maneuvers. Thermal protection. Heat shields on the nose and belly absorb or radiate heat, protecting internal systems. Here's the operational advantage. Range. Boost glide systems can fly thousands of kilometers. Examples include China's DF-17 with DF-ZF glide vehicle, about a 2,500 kilometer range. Russia's Avangard intercontinental range, 6,000 plus kilometers. US systems like LRHW and CPS, 1,700 to 2,700 plus kilometers. Speed, sustained Mach 5 to 10 plus across the entire flight. Maneuverability, can adjust course mid-flight, complicating interception. Here's why this works. No engine means no combustion instability, no fuel to carry, no millisecond mixing problems. Simpler, more robust design. You trade powered flexibility for proven reliability. Here's the current arsenal. China fielded DF-17 operationally. Russia deployed avant-garde ICBMs with HGVs. US Dark Eagle LRHW entering service. Navy CPS in development. Boost Glide isn't experimental, it's operational. Here's an analogy. Imagine two ways to cross a canyon. Option 1. Build a rocket-powered jetpack that flies you across while burning fuel the whole way. Scramjet. Option 2. Get launched from a catapult, then glide across on wings without an engine. Boost Glide. Option 1 is cooler. Option 2 actually works. Section 4. The trade-offs. Engine versus no engine. Alright, both systems stay hypersonic, but they have completely different strengths and weaknesses. Let's compare directly. Feature, Scramjet, Boost Glide. Power source, air-breathing engine, one-time rocket boost. Range proven, 200 seconds powered flight, X-51, thousands of kilometers operational. Speed, Mach 5 to 10 sustained in theory, Mach 5 to 20 plus proven. Flexibility, can theoretically loiter but just and re-attack. One-shot trajectory, limited adjustments. Complexity, extreme combustion, cooling, and materials. Moderate heat shields, guidance, control. Operational status, experimental demos only. Fielded by China, Russia, and US. Here's the scramjet advantage in theory. If you could make scramjets work reliably, you'd have sustained powered flight. Fly around defenses, loiter, choosing attack timing. Smaller boosters, less weight, easier to deploy. Reusable platforms, potentially, air launch from bombers. That's the dream, but it's still a dream. Here's the Boost Glide advantage in practice. Rocket boosters are mature, proven technology. Thermal protection systems are well understood from re-entry vehicles. Guidance and control at hypersonic speeds is challenging but solved. Result, you get operational weapons now, not decades from now. Here's the strategic reality. Countries building hypersonic arsenals today are choosing Boost Glide because it works. Scramjets remain in research labs because they're too finicky for combat. Here's an analogy. Scramjets are like fusion power, always 20 years away, theoretically revolutionary and practically elusive. Boost Glide is like solar panels, not as sexy, but they work today and you can deploy them at scale. And in warfare, works today beats perfect tomorrow. Section 5. Which approach is winning? Alright, so which approach is actually winning the hypersonic arms race? The honest answer? Boost Glide, and it's not close. Here's the scorecard. China, DF-17 with DF-ZF glide vehicle, operational since 2019. DF-21D anti-ship variant, reportedly operational. DF-26 with maneuverable warheads, deployed. Russia, avant-garde ICBM with HGV, operational since 2019. Kinzhal air launch system used in Ukraine, though debated if truly hypersonic glide or just fast ballistic. United States, Dark Eagle LRHW, first units activated, live missiles by 2025. Navy CPS, in development, shared components with LRHW. Air Force programs, various hypersonic cruise and glide concepts. Scramjet weapons, 0 operational systems publicly known. Here's why Boost Glide dominates. Reason 1, it works. Rocket technology is mature. Glide bodies are testable, heat shields are solvable. Reason 2, it scales. You can build dozens or hundreds of Boost Glide missiles using existing manufacturing. Scramjets require exotic materials and precision engineering that don't scale easily. Reason 3, it's survivable. Boost Glide systems are simple enough to work under combat stress. No fragile combustion to maintain. Here's what this means for missile defense. Current defenses, Patriot, THAAD, Aegis, are optimized for ballistic missiles with predictable trajectories. Boost Glide vehicles maneuver unpredictably, approach from unexpected angles, travel too fast for most intercept geometries. Defending against them requires early detection, space-based sensors, faster interceptors, potentially scramjet-powered, ironically, layered systems with multiple chances to engage, all of which are expensive and not fully deployed. Here's the future. Scramjets will continue development. Eventually, they might work reliably. But for the next decade, Boost Glide will remain the dominant hypersonic strike technology, because in weapons development, good enough today beats perfect someday. Conclusion and CTA. Summary. Alright, let's wrap this up. Scramjets and Boost Glide vehicles both stay hypersonic, but only one actually works in combat. Here's what we covered. Air at Mach 10 acts like concrete. Shockwaves, plasma, thousands of degrees, both systems face this barrier. Scramjets try to breathe air at Mach 10 by burning fuel in supersonic flow. NASA's X-43A flew for 12 seconds at Mach 9.6, still experimental after decades. Boost glide. Rocket boost to the edge of space, then glide and maneuver at Mach 5 to 10 plus for thousands of kilometers. Operational in China, Russia, and entering U.S. service. Trade-offs? Scramjets promise sustained powered flight but remain too complex. Boost glide delivers proven range and speed with simpler technology. Who's winning? Boost glide dominates current arsenals. Scramjets remain in labs. Here's the one-line takeaway. Scramjets are the Formula One cars of hypersonics. Beautiful, temperamental, stunning on test day. Boost glide is the armored truck that's already hauling explosives across continents. Final thought. Sometimes the hardest engineering loses to the smartest physics. Scramjets fight the hypersonic problem. Boost glide exploits it. And in the real hypersonic arms race, exploitation beats innovation, at least for now. You made it to the end. That means you wanted the engineering reality, not just hype. Here's what I need. Like this video if I explained why scramjets are hard and boost glide dominates. It helps others find real analysis. Drop a comment. What surprised you? The X-43A's 12-second flight? The boost glide simplicity? The operational gap? I read every comment. Subscribe. I break down military technology like this, what actually works, what doesn't, and why. No hype, just physics and strategy. Coming next. Why intercepting hypersonic weapons is almost impossible. The detection, tracking, and geometry problems that make defense the losing game. You clicked for answers, you got them. Keep learning. See you next time.